Hello everyone, first of all, I would like to thank the organizers for providing me with this valuable opportunity to share my research findings and views with you in such a distinguished forum. I'm a postgraduate student from Hunan Institute of Science and Technology. It's a great honor for me to stand here and share my research on hyperspectral object tracking. As shown in the figure, the left side is a normal RGB image and the right side is a hyperspectral image. And based on the spectral reflectance at positions 5 and 6 in the figure, it can be seen that there is a large difference between the spectral reflectance of plastic toys and closed doors. It shows the potential to outperform conventional RGB-based tracking methods, especially in complex scenarios. Most of the existing deep learning methods borrow from multimodal tracking, using false color images as input to the RGB-based tracker, and externally designing an additional hyperspectral feature extractor before fusing the information, for example TRTS and HNet. However, it's difficult to train a robust tracker due to the insufficient size of the dataset. Compared to common RGB tracking datasets, hyperspectral datasets are not of a magnitude. So, is there an efficient way to make the tracker perform well even with small datasets? In recent studies of multimodal object tracking, a prompt learning approach that utilizes an RGB-based model and freezes the parameters of the tracker network delivers the knowledge of the model to adapt to the downstream task. The lower two network structures are applications of prompt learning for multimodal object tracking. These methods are simple and effective. Prompt learning does not require a lot of data compared to the fine-tuned approach, and based on this, it can be a good solution to the situation of insufficient data. Our proposed tracker uses prompt learning approach to adapt to hyperspectral datasets, similar to VIPT. In the encoder stage of transformer, false color features and hyperspectral features are fused externally through prompt module. The basic tracker uses SIGTrack. The weight model trained on RGB dataset is used and frozen. The most significant difference compared to VIPT is that we have weighted the prompt information, taking a more moderate approach to prompts. Specifically, we multiplied the residual portion of each prompt modular by lambda, when lambda has an initial value of 0, and then increase lambda in a fixed step and fix it when lambda was 1. A lot of prompt related work, for example VTP and MAPLE, is done by adding some additional learnable tokens in the transformer structure, where these learnable tokens are initialized to 0. So we borrow this idea in our network design. For the experimental part, since the dataset provided by HOT2023 consists of 3 different numbers of brains, we trained 3 models to adapt to different brains of data, modifying only the number of channels in the input and keeping the subsequent network parameters unchanged. Here, we selected RGB-based tracker SIGTrack as our baseline and compare it with some RGB-based trackers. These trackers were tested on false color or proposed VP HOT additionally utilizes hyperspectral information. Our method achieves the best results in different brains of data and requires only 1.7 million learnable parameters. In order to verify the validity of our idea, we compare it with the approach in the VIPT. In the figure A, shown for the VIPT approach, figure B is our method, and figure C is the combination of both. After ablation experiments, our method is optimal. The results are shown in Table 2. In addition, we also investigated the impact of different step sizes on the results for the step size, as shown in Table 3. Finally, our proposed scheme has the potential and achieved the 5th place in the competition, but due to the equipment, we were only able to experiment on best 256 model. Thanks all for listening.